Hey guys, this lesson is 9.5 from Calculus BC, and this is the test for alternating series. So in a previous video, we said that seeing this -1 raised to n or -1 raised to n plus 1 lets us know that our signs on each term is going to alternate, like positive, negative, negative, positive. This just determines whether we start with a negative or a positive, okay? So this one's really easy to spot. And what the test is going to tell us is it'll tell us if the series converges if we can prove these three. 1, that it alternates, which is really easy to spot. 2, if the limit as n approaches infinity of a sub n, which a sub n is the other part of the series, not including this portion, if it equals 0, and if the terms of this series decreases, okay? So nice and easy. Let's take a look at this first one, okay? First question is, does it alternate? Okay, well, I can spot that right there, so my answer is yes. Next is, does the limit as n approaches infinity of a sub n, which a sub n is just this portion, 1 over n, does it equal 0? Well, this gives me 1 over infinity. This is bottom heavy, so this equals 0. We're good. And last is, does a sub n, which 1 over n, does it decrease? Well, let's check it out. First, we'd get 1 over 1. Then we'd get 1 over 2. Then we'd get 1 over 3, and so on. Okay? So if my denominator continues to get bigger, that means my numbers will continue to get smaller. Therefore, it is decreasing. So if you can prove 1, 2, and 3, you can now state, therefore, this infinite series, I'm just going to rewrite it really quick, converges. And you're done. You might be thinking to yourself that in and of itself, each of these tests are fairly simple. Where this becomes difficult on the AP tests or on a chapter test is where, if they're all mixed up in the bunch, is memorizing these rules and being able to catch which series you're testing and then being able to follow the steps for each. You'll notice that on most of these questions that we have been looking at, except for the geometric, we only determine whether it converges or diverges. We haven't necessarily found out what it converges to, what number, okay? So what we're going to see next is, even if we can't figure out what number it converges to, we are going to be able to find a range of numbers that it'll converge to, okay? And we're going to use the alternating series remainder to do this. So here are the 3 steps that we're going to do, okay? First, we're going to solve for the partial sum, okay? Then we're going to solve for what's called the remainder. The remainder is found by finding the following term. So for example, if they want us to use 6 terms, we'd find the 6th partial sum, and then we'll find 6 plus 1 would be the 7th term, the following after. And then we can set up the range. So the sum would be somewhere in between the partial sum minus the remainder and the partial sum plus the remainder, okay? Looks really fancy with this notation, but let's check it out. I promise it's not that bad, okay? The example says, if the series converges, approximate the sum by its first 6 terms, okay? So remember, anytime they use the word series, that just means the sum, the summation, okay? So by looking at this, the first thing I have to do is test that it converges. I got to prove it, okay? So I can spot that I'm going to use the alternating test because I see this symbol right here, right? So this is going to tell me that it alternates, okay? The second thing I need to check is the limit as n approaches infinity of a sub n, which is what's left over, which this is going to give me 1 over infinity factorial, which is an even bigger 1 over infinity, which is bottom heavy, so this equals 0. I'm good. And then third, I need to check that the terms of a sub n of this portion decrease. So if I'm working with 1 over n factorial, first term would be 1 over 1 factorial. Then I'd have 1 over 2 factorial. And then 1 over 3 factorial. And as you can see, my denominator is getting bigger and bigger and bigger every time, which means that it is decreasing. So I just proved, right, based on these three, I just proved that this converges, okay? Now that I've proven that it converges, I can find the range of numbers of which it converges to. And it tells me here in the given to use the first 6 terms to find this, okay? So now, draw a little line here. Step 1 is to find the partial sum. So step 1 is going to be to find S sub 6, the sum of the first 6 terms, okay? My first term, I'll analyze my sign in a moment. Let's look here really quick. It's 1 over 1 factorial. Now, if I put a 1 in this spot at the end, 1 plus 1 is 2. An even number is going to make this positive, okay? Now, my next term is going to be 1 over 2 factorial. And then putting in a 2 here, 2 plus 1 is 3, is going to keep this odd. And because it alternates, you don't really have to go crazy overthinking this. You just know it's going to be positive, negative, okay? Once you know which one it starts with, you're pretty much set for the rest. So I know this one will be positive. And now I have 3, so 1 over 3 factorial minus my fourth term, 1 over 4 factorial plus 1 over 5 factorial, and then minus 1 over 6 factorial, okay? Now, feel free to go to your calculator for this. I'm a fan of keeping it as a fraction for now because decimals you may end up rounding too soon. So on your calculator, this gives you 91 over 144, okay? Step 2 is going to be to solve for r sub n. So if I'm doing the 6th term, I would say r sub 6, which means a sub 6 plus 1, which is saying a sub 7, which just means I only want the 7th term, okay, which will be negative 1 raised to 7 plus 1 times 1 over 7 factorial, okay? 7 plus 1 is 8. That's an even number, so this will be a positive, okay? I'll put a little plus sign here so we don't forget. And then 1 over 7 factorial you can also put on your calculator, and that gives you 1 over 5,040, okay? So now my last step is going to be to create that range, okay? So I'm going to say the sum, which was that 91 over 144, minus my r sub n, which was 1 over 5,040, is a smaller number of my range for my sum, and then my larger number is going to be them being added. Okay, you can leave your answer like this, but if multiple choice options like on an AP test might have this cleaned up as a fraction or decimal. So this gives you around 0. Let's move this up. 63174 and 0.63214. That means that this series, this alternating series, will converge to a number that is somewhere in between, okay? And we found that based off of the 6th term. With alternating series, we have 2 scenarios, one where they could absolutely converge, and that's if the alternating series converges and the absolute value of it, meaning ignoring the change of signs, also converges. And then we have what's called a conditional convergence, which is if the alternating series converges, but the absolute value of it does not. Okay, so let's look at this first question. Does the series absolutely or conditionally converge? So initially, if you look at this, it may not look like an alternating series, but I want to remind you that the graph of sine goes from +1 to -1, and it goes over and under, and it keeps doing that over and under again and again and again, which means it's going to alternate from positive to negative. Okay, so I first need to test if actual a sub n, meaning if this alternates. So we just said based on the sign, it does alternate. Okay. 2, I need to test that the limit as n approaches infinity of the portion not alternating. So if I don't take into account these positive and negatives, I'm going to get fractions times 1 over that n squared. Okay. If I plug in just into the 1 over n squared and infinity, I get 1 over infinity squared, which is bottom heavy, which is 0. Okay. And if you did take into account those numerical values, not signs, that the sign would bring in, it'd be a fraction, right? And anything times 0 would still be 0. So it would still work out the same. And then third is to check if the numbers are decreasing. So again, we're going to put that sign on hold, and we're just going to look at that 1 over n squared, okay? And that's going to be 1 over 1 squared. Then it's going to be 1 over 2 squared, 1 over 3 squared. And that, as you can see, the denominators are getting bigger, which means my number is going to get smaller. Now, if I multiply it by the fraction that sign would give me, right? Here less than 1, here less than -1, it would still, multiplying a fraction by another fraction is going to make it get even smaller. So, because the numbers are getting smaller, it is decreasing. Okay, based on these three, I can say that this original one here converges. All right, so I tested the first part. Now I need to see if the absolute value will also converge. So I'm going to say absolute value of sine of n over n squared. Okay, so n squared will always be positive. So I don't have to put that part in the absolute value brackets, okay? I'm going to rewrite this just so we get a better idea. I'm going to put absolute value of sine times 1 over n squared. And again, I can take that 1 over n squared out of my absolute value sign because anytime I square anything, it's already going to be positive. If I take a minute to analyze this absolute value sign, it's like looking at this graph and saying that all of the negatives would then become positive. So my sine of n, absolute value of it, are going to be values that are in between 0 and 1. So less than or equal to 1. So if I replace that here, that's going to be some sort of a fraction, like let's say 1 over some number, okay? Times that 1 over n squared. Now, if this is a coefficient, I can rewrite this on the outside. And what I'm really working with is 1 over n squared, which is a p-series. Now, I want to work, if I'm going to compare with this p-series, I'm doing a direct comparison now. I'm going to compare it with the original. So, if this value, right, the original, is being compared here with 1 over n squared, I can see that my denominators are identical, n squared. So now I'm going to move to comparing the numerators. Sine and 1. Now, if we look at their graph, I know sine will give me numbers equal to 1 or less than, and this one will always be 1, which means that this one is going to be bigger. So, since sine of n over n squared is smaller than 1 over n squared, I'm testing the bigger one, which means I can only I'm testing the larger. I can only test for convergence. Okay? So now let's test this one. If this is P series and my P is 2, okay, and 2 is greater than 1, then we can say it converges. Okay, so let's recap. We said that the actual series converges. Then we went to see if the absolute value converges. We had to do a comparison and we tested 1 over n squared. Since we were testing for convergence and we got convergence, we can say that the absolute value also converges. Okay? Now, one more time. If the original converged and the absolute value converged, because both of them converge, I can say that this original question absolutely converges. And again, that's because both the original and the absolute value converge. All right. Let's look at these last two questions here. I see that they're both alternating. So I'm going to first test the convergence of the series that's given, which is an alternating. And then I'm going to check the absolute value of them to then check if it conditionally converges or absolutely converges. So starting here, I'm going to test the original. It's obviously alternating because of what's in the numerator. I'm going to test the limit as n approaches infinity of what's left without this. If you want to rewrite it to see it a little better, you can bring this to the front and then say times 1 over n. It's a little easier to see what's left, okay? And if I plug that in, I get 1 over infinity, which is bottom heavy, which equals 0, which is what I'm looking for. And then if I'm testing that leftover, that a sub n, I want to confirm that it decreases, sorry. So 1 over 1, and then 1 over 2, 1 over 3, and so on. Because my denominator is getting larger, I know my numbers are getting smaller, therefore it is decreasing. So, based on this, the original is convergent. It converges, okay? So now I'm going to draw a line. I want to test the absolute value. So the absolute value is really just going to eliminate this numerator because all this numerator does is alternate my sign. So that means what I'm really working with is 1 over n. Okay? 1 over n is harmonic. And we know that harmonics diverge. Okay? So because the original converged, but the absolute value diverged, we can say that this is conditionally convergent. Let's look at this last one. Again, straight from the beginning, I can see that this is an alternating series based off of the numerator. So first I'm going to check if this converges, okay? If you want to rewrite it, you're more than welcome to. You do not have to. I personally like to see this up front So I could see what my a sub n, my leftover is, which I can call it square root of n, or I could say n raised to 1/2. Okay? So to begin with, is this alternating? Yes, it is. You can see that right here and right there. The limit as n approaches infinity of my leftover, which is my a sub n, 1 over n to the 1/2. I get 1 over square root of infinity, which is 1 over infinity, which equals 0. That's what I was looking for. And then I want to check that this is decreasing, okay? So if my leftover, my a sub n, is 1 over square root of n, I get 1 over square root of 1, 1 over square root of 2, 1 over square root of 3, 1 over square root of 4, and so on, okay? So if you want to double check this in your calculator, feel free to, but my denominators are getting larger, which means my numbers are getting smaller. Therefore, this decreases. Okay, so I've proven that this alternating series converges. I'm going to draw a line to now check if it is conditionally or absolutely convergent. I do that by testing the absolute value of the original. Oops, sorry about my E there. Okay, so the absolute value is just going to eliminate that numerator, okay? And I'm going to be left with 1 over, you can write square root of n or n to the 1/2. Again, this eliminates because all this does is change the sign. So I'll be left with a positive 1 because of the absolute value. And this square root was already positive, so it's going to stay positive. Now, if I check this question, this here is a P series where my P is 1/2. And because that is less than 1, this diverges. Okay, so since I got convergent on the original, the alternating, and divergent on the absolute value, this one is also conditionally convergent.